Hello, Professor Jarahi. I think Professor Jarahi is with us now today.
Yes, hi. Hope I am not late.
Hello, Mona. How are you?
Hi, Gunesh. Good. How are you?
I'm good, thank you. No, you're just right on time.
Okay, good. Nice meeting you.
Likewise, I'm pleased to see you, and thanks a lot for accepting our invitation.
Sure. Thanks for your invitation. My pleasure.
So, Professor Ganesh, shall we start?
Sure. Let me share my slides.
Perhaps we can wait for 4 minutes.
Yep. I think
Professor Ganesh, can we wait for a couple of minutes?
Yeah. In fact, I know that Professor K will be tuning in, so let's wait for a couple of minutes first. So Mona, I'm afraid to ask, but how is the weather there?
Well, pretty warm. Actually, today is 78 Fahrenheit. Tomorrow is 84 Fahrenheit. I think it decided to be spring now.
Oh, excellent.
Really. What about there in Montreal?
Yeah, it's today was -6 and I was feeling very happy about it.
Oh, okay. Well, you see seasons.
Yeah.
That is something that we really miss
That is,
here.
yeah.
Yeah.
Next time, perhaps we can invite you in person.
Yeah, I look forward to it. I love Montreal. I haven't seen Montreal in winter, but I can imagine it just gets nicer in snow.
It's different. Yeah, it is nice for sure in the Christmas time. Hello, Kay.
Hello.
How are you?
Hello, Mona. How are you
Hi,
doing?
Kay. Good. How are you? Good seeing you.
Good. Nice to see you here. So,
Yeah.
thank you very much for the for this presentation for this entire group here. Of course, I heard that for goodness that you want to come to Montreal during winter time. That's
Yes. Yeah. Why not? I was there for IMS. It was summer. It was nice.
Yeah,
but
that's right. That's right. That was 2012. I organized, but but it was very hot actually during IMS 2012.
Yeah.
Exceptionally hot. I don't know why, but it's usually the temperature could be very mild, but winter is another story. Okay, but I'm sure you'll love that if you like ski, for example.
Well, I love snow. I was in Michigan for some time, and
Michigan
yeah, I must say, snow was nice.
Well, Michigan has more snow actually than Montreal, I believe.
I see.
Because that's a lake effect. They call it.
Mm-hmm.
Hello, everyone. Here I am, just gotten home right now. I'm so sorry for my inconveniences. And my apologies, by the way. I should be here a couple of minutes at least ahead of time. And thank you.
No, Mansur, no worries. We are in good shape.
Don't worry, we had a good chat here. So
yes.
Yeah, that's a great pleasure to have another bright mind from a flagship research group, Professor Mona Jarahi. Of course, Dr. Gunesh has a lot to say about this workshop series as she's serving as the workshop chair for these interesting events. And so without any delay, I think we should hand over microphone first to Dr. Gunesh to introduce our respective speaker. And then we will proceed with the talk with Professor Mona Jarahi. So thank you, and I'm sorry for the inconveniences that happen right now. So we are waiting for you. Floor is yours, Professor Gunesh.
Oh, I was muted. So welcome everybody to this third edition of the Terahertz Day. And I would like to just briefly discuss about what we have been doing so far. And I am the workshop chair, and this is a workshop that my name is Gunesh, and I'm with Polytechnic Montreal, and we want to focus on the application of terahertz bands, and we are investigating it from different perspectives in this workshop series. Oh, oops, sorry, went too far. Now I am at Polygram Research Center, and our director is Professor Ke Wu, and we are also happy to have him here. So in this, in one of the say most equipped research centers, our intention is to investigate the applicability of terahertz series bands for future applications, and we are looking at it from different perspectives. And this workshop series is trying to address these different research directions, and we are trying to learn from the experts in the fields. Why the terahertz? The potential is obvious to almost everyone, but of course the challenges are also obvious. We have a lot of freedom in terms of the bandwidth and unlicensed bands, and also the potential of smaller antenna sizes. And it has provides sustainability for integrated terrestrial airspace networks. And the goal of our workshop series is to investigate this hidden potential and understand the research activities going on in complementary yet different fields. Now, our first speaker was Professor Angeliki Alexiou, and she gave us a very interesting perspective from the network deployment perspectives towards the 6G era, including some measurements. We were happy to host her in this workshop series. And our second speaker was Professor Christophe Kreyer from Université Catholique de Louvain, and he also talked about the potential of the metasurfaces, especially, and the synergy between these antenna designs with these challenging frequency bands. Our third invited speaker is we are happy to host Professor Jarrahi here, and it is my pleasure to introduce her today. So it's a long biography, but I would like to highlight a couple of things from this extremely impressive biography. Professor Jarrahi received her bachelor's degree from Sharif University of Technology in 2000, and her master's and PhD degrees from electrical engineering in electrical engineering from Stanford University. She served as a postdoctoral scholar at the University of California, Berkeley, and she later joined as an assistant professor to the University of Michigan, Ann Arbor later. And now she's with the University of California, Los Angeles since 2013. And she's serving as the director of the Terahertz Electronics Laboratory. She has made significant contributions to the development of ultra-fast electronic and optoelectronic devices and integrated systems for terahertz, infrared, and millimeter wave sensing, imaging, computing, and communication systems. And by the use of novel materials, nanostructures, and quantum well structures. And she has numerous publications, over 200 publications, and she has given again numerous speeches, and her work was also introduced to the public through numerous outlets. So it's not only the academic world that she's informing, but also targeting news outlets, including Popular Mechanics and Huffington Post. She has received I believe almost all prestigious awards that you can think of, starting with the Presidential Early Career Award for Scientists and Engineers, and Frederick William Bessel Research Award from Alexander von Humboldt Foundation, more in Inventor Fellowship from the Gordon and Bessie Moore Foundation, Calvi Fellowship, and followed with a number of distinguished awards. She's a fellow of IEEE, OSAs, SPIA, and IOP societies, and she has served as a distinguished lecturer of IEEE, traveling lecturer of OSA, and visiting lecturer of SPIA society. So we are really happy to have you here, Mona. Thanks a lot for accepting our invitation, and we are looking forward to your talk. Mona, you are muted.
Thank you very much, Gunesh, for your kind introduction. So let me share my slides, and I would like to thank you again for inviting me to this exciting workshop. So Gunesh, you mentioned the previous speakers, their focus of presentations. My talk would be more focused on optoelectronic devices for mainly generation and detection of terahertz radiation, and some imaging, spectroscopy, spectrometry applications that we have been pursuing with it. As Gunesh mentioned, terahertz spectrum has a lot of unique applications. So they're really enabled by unique functionalities of terahertz waves. So basically, many optically opaque materials are more transparent to terahertz waves. So one can access visually inaccessible environments with terahertz waves, not all of them, some of them. A lot of materials have, a lot of chemicals, molecules have unique spectral responses to terahertz radiation, and that allows you to identify these chemicals in a non-invasive way. In fact, more than 98% of the entire photons that exist in our universe lie in the terahertz frequency range and carry a lot of information about formation of stars, planets, galaxies, and their dynamics. And many of these information are obscure to infrared and visible radiation because they happen in dusty cloud environments. As a result, terahertz waves are great tools for astrophysics studies as well. Obviously, as we also move to higher frequencies as signal carriers for communication, we can have broader bandwidths, we can accommodate higher data rate communication systems, which obviously is a great direction that everybody in communication industry is looking for. But unfortunately, where the terahertz frequencies are located in the spectrum between optical and electronic regime, it causes some challenges to make systems to work in this frequency range, mainly because transistors that cover the lower frequency band in the millimeter wave and radio frequency range cannot really operate efficiently as we come to the terahertz range. And also many laser concepts that work very well in the visible and even infrared range, they have serious challenges when we want to scale the operation to terahertz. And here it's out of the scope of this discussion. There are, for very good physical reasons, that these laser and transistor technologies cannot cover the entire terahertz band. And if you would like, in the question and answer part, we can discuss more detail if you want to know about it. So while both electronic and optical communities are trying to push the frequency of transistors and lasers to cover the terahertz band, one other, I would say, detour around the problem is to benefit from excellent optical devices that are already available and find ways to basically convert the radiation to terahertz frequencies or benefit from them to detect terahertz radiation that I will describe right now. So so in this sense, for example, if we want to make a terahertz source, we are not making a fundamental oscillator. We are trying to build an efficient optical to terahertz converter, which can be done two ways. Either one can use a nonlinear optical medium to interact light with that medium to generate terahertz radiation, or one can use a photoconductor to convert light to terahertz radiation. So in the first case, a nonlinear process, either it is frequency difference generation, parametric oscillation, you name it. The process is a photon to photon interaction process, meaning that a terahertz photon, when it interacts with the nonlinear medium, generates a terahertz photon, but that would be accompanied with at least another photon. And because the energy of terahertz photons and optical photons are very far from each other, most of the energy will be carried in an idler optical photon that is generated. So because of this single photon to photon interaction process, even though we get 100% quantum efficiency, meaning that 100% of optical photons convert to terahertz photons, still there is a big reduction in energy efficiency because energy of terahertz photons are much less. This is called the Mandry-Rowe limit, which is a fundamental limit that reduces the efficiency of nonlinear optical to terahertz converters. So in my group, we are using nonlinear processes, and one approach that we use to tackle this Mandry-Rowe limit is to basically engineer cavities that basically we recycle the generated optical photons as a result of nonlinear process, and then we can recycle it to improve the efficiency of the process. The other approach, photoconductive approach, operates different. One important thing I forgot to say is that the optical beam that we use to excite the nonlinear medium has terahertz frequency information embedded in it, and that's how we can get terahertz radiation. So there are two ways, general ways, one can embed terahertz frequency information in light waves. One is using a short femtosecond light beam, where its envelope will be very short in time, which means in frequency domain, it will be very broad. So it contains very broad frequency ranges covering the terahertz range. Or one can get two continuous wave optical beams, spatially overlap them, for example, in a fiber, or spatially other ways. And that way, if their frequency difference is around terahertz frequencies, they beat their envelope, beat each other at terahertz frequencies, and then again, we can generate CW terahertz light. So in the photoconductive approach, we take the same approach, meaning that we embed terahertz frequency information in our light. We have a photo-absorbing semiconductor that absorbs these photons, generates electron-hole pairs, and when we apply an external bias field, we can accelerate separate carriers, make a time-variable dipole moment that radiates terahertz waves. This approach is specifically interesting in the sense that because photons are first converted to charges, and then those charges are accelerated and generate radiation, and because one pair of electron holes, we can generate multiple terahertz photons through an antenna, the optical to terahertz conversion efficiency through this technique can technically be more than 100%. So it can be very efficient compared to nonlinear processes. Please don't think by this statement on violating any conservation laws of energy. Remember, we have another external bias voltage that we apply to the system. It injects its own energy. So optical to terahertz conversion efficiency can be more than 100%, while the overall efficiency of the system obviously cannot exceed 100%. That being said, when we started working with these photoconductive devices, the efficiencies were nowhere close to 100%. Still, they're not. But I will explain there are, for good physical reasons, that this challenge existed, and we have basically found ways to use metallic nanostructures, plasmonic nanostructures to make this light matter interaction more efficient. And now we are reaching to optical to terahertz conversion efficiencies around 12%. Still, there is a lot of room to improve, but already through these enhancement methods, we were able to enhance efficiencies by 3 orders of magnitude. I just want to mention that in terahertz wave detection, also these concepts are reciprocal. So I can reverse operate the same concept to detect terahertz radiation. For example, if I want to detect a terahertz wave through a nonlinear process, I let the received terahertz radiation and optical beam, where again I embed terahertz frequency information in it, interact with each other in a nonlinear medium. And now, as a result of that terahertz photon and optical photon interaction, I generate another optical photon, which is usually called idler, that this idler carries information about intensity and frequency of the received terahertz radiation. Again, because it's a single photon to photon process, the efficiencies can be limited. In the photoconductive case, again, is reciprocal detection process. So we shine light on the photo-absorbing semiconductor, generate whole pairs. We don't bias the photoconductor. We let the received terahertz field accelerate and drift the carriers, and we measure the photocurrent that is induced as a result of that process, which again carries intensity and frequency information of terahertz waves. Again, this process can be very efficient, but because of low efficiency interaction of light and matter, the efficiencies used to be very limited when we worked on it. But I will show that now we are able to get close to quantum level sensitivities at room temperature by plasmonic enhancement methods that we use. Before mentioning our approaches, I just want to mention that photoconductive terahertz generation techniques are usually implemented like the diagrams I showed were very conceptual diagrams. In real world, there are basically antennas that interface terahertz radiation with the device. So if we want to generate pulse terahertz radiation, we generally excite a semiconductor region sandwiched between antenna electrodes, where when we shine light, we generate electron hole pairs, we accelerate them, couple them to antenna, and the current that is induced as a result of this process, which is a pulse photocurrent, will generate terahertz pulses. If we want continuous wave terahertz radiation, we excite the device with 2 CW heterodyne beams with a terahertz beat frequency. So as I mentioned, when we started working on these devices, the efficiencies, optical to terahertz conversion efficiency was very low. And that was because if we want to have very efficient operation, for every electron hole pair that we absorb, we want to quickly transit them to the antenna to radiate terahertz waves. When I say quickly, I'm talking about time scales that are much shorter than terahertz oscillation cycle. The problem is that terahertz oscillation cycles are in picosecond or sub-picosecond time scale. If I want to move carriers too fast in my semiconductor, I'm limited by the scattering of carriers in the semiconductor. Most semiconductor substrates give me velocities for carriers that saturate after you accelerate carriers more than a certain extent. So generally, you cannot get a sub-picosecond transit time for carriers if the transport path distances are more than a few tens of nanometer, which means generally the conventional systems only benefited from carriers that were generated within few tens of nanometer distance from antennas. And as a result, most of the light was not really utilized in an efficient way. Also in the detection process that I said is a reciprocal process, the same problem exists. So what I will come back to this, what my group has done to basically bypass some of these limitations was embedding different metallic nanostructures and plasmonic nanostructures in the active area of the device where light and semiconductor, light interacts with the semiconductor. So what we do is that we deliberately confine light into regions that have very short distance to the radiating elements. And by exciting surface plasmon waves, we do this coupling in an efficient way. So if we don't have any control to make the velocity of carriers faster in the substrate, at least we can make their transport path length shorter to get better efficiencies. So just want to mention, since I mentioned pulse terahertz radiation generation and CW generation and detection, just want to mention that pulse systems are generally useful for spectroscopy applications that deal with broad spectral signatures like solids and liquids, and also imaging applications where depth information is important, because when you do imaging with terahertz pulses, by monitoring the echoes of the pulses from different layers of the object, you can get information about layer by layer structure of the object. However, if one wants to do very narrowband spectroscopy, like gas spectroscopy, or in astrophysics applications, looking at spectral signatures of gases, or in communication application, one needs to use basically CW systems, which are called frequency domain systems, to maintain that high spectral resolution. So back to the ways we have utilized these plasmonic nanostructures in our terahertz devices. This was the first demonstration that we had where we built two antennas with and without plasmonic structures. And we noticed that we would be able to get 50 times enhancement in terahertz radiation power because we are able to utilize carriers in a much more efficient way. So here, for example, if you look at the photocurrent we coupled with a terahertz antenna, you see that we have a 7 times enhancement in photocurrent. It is because of better utilization of photocarriers. And because radiation from an antenna has a quadratic relation with the current you feed to it, we see basically 50 times enhancement in the radiation power. So as the first demonstration, when we use the same devices in a terahertz detector scheme, we were again able to see about 30 times enhancement in detection sensitivity that exceeded a bandwidth of more than 1.5 terahertz. So this was really the beginning of our work that showed the impact of plasmonic structures. And after that, we got more targeted to build these plasmonic antennas for specific applications that have very targeted functionalities. For example, one of the great needs that we have in telecom or compact systems is to make systems that work with telecom lasers at 1550 nanometer wavelength. And also it's important to have a very broadband radiation and broad tunability. So here we were able to show that our plasmonic terahertz antenna platform has all these flexibilities, meaning that, for example, by changing the specific substrate that is absorbing photons, for example, here, indium gallium arsenide doped with erbium arsenide, we are able to absorb telecom light, which means we can have a very compact system. And by using a log spiral antenna, we were able to enhance the bandwidth of the system. So in this case, we are exciting our antenna this time with continuous wave terahertz optical beam that has continuous wave terahertz information embedded with it in it. And you can see that we can get very broad tunability in our terahertz frequency, all the way from 0.2 terahertz to 2.5 terahertz with powers that reach a milliwatt around 1 terahertz. So that shows the flexibility of the design to offer different bandwidths, polarizations. In this case, this would be circularly polarized wave, and operation at different wavelengths. So one can also put these plasmonic devices with nano antennas inside an array and create a phase array concept that we really benefit from it in millimeter wave and radio frequencies. So for those of you that work on phase arrays, you know, as we go to higher and higher frequencies, a practical challenge is to make sure the attenuation and is basically uniform along the array. We want to make sure the phase differences are maintained to be basically varying linearly, and it becomes very hard as you go to higher and higher frequencies. These optically excited antennas have advantages in the sense that because the excitation is optical, it's very easy to introduce those phase modulations, phase tilting in the optical domain. So since the phase of the generated terahertz radiation follows the phase of light, by using different kind of spatial phase modulators for light, we can tilt the phase front of the optical beam, and that results in tilting the phase front of the terahertz radiation. So in this particular work, we have an array of 3 by 3 plasmonic nano antennas coupled with log spiral terahertz antennas. We use micro lens array to focus lights individually on the active area of each device. And as I mentioned, not only we can enhance the overall terahertz power by combining the radiation power of all individual antennas, but also we are able to tilt the terahertz radiation or do spatial beamforming by directly doing spatial beamforming and phase front tilting on the optical side. Another modality that we have tried was using alternative plasmonic structures to enhance light matter interaction even further. So if you remember in the first proof of concept design, I mentioned we got 50% enhancement in optical to terahertz conversion efficiency. And in that case, our plasmonic structures were metallic structures placed on our substrate. So in this work, we have engineered specific plasmonic nanostructures that are 3D in nature. Basically, there are arrays of these slab waveguides formed by the gratings. And through that, by exciting higher order resonance mode in these slab waveguides, we are able to get even stronger light matter interaction and while absorbing a major fraction of light within the areas between the nano antennas. So through this method, we were able to enhance optical to terahertz conversion efficiency by another order of magnitude by making this enhancement more efficient. So here I'm comparing two devices. They're both using a log spiral antenna, a terahertz antenna, like the one I'm showing in this picture. One of them, the red curve, is using 2D plasmonic structures, basically 2D gratings placed on my semiconductor substrate connected to the antenna electrodes. In the blue curve graph, we are using the 3D plasmonic structure, which you see the schematic here in the inset. So as I said, because with the 3D plasmonic structure, we can absorb light closer to the electrodes that are connected to antenna, we were able to get an additional order of magnitude enhancement in optical to terahertz conversion efficiency. And we were very excited that at 110 microwatt at 1.5 milliwatt terahertz power, sorry, 1.5 milliwatt optical power, we were able to generate 110 microwatt terahertz power, which is 7.5% optical to terahertz conversion efficiency. I must say that here we have a silicon lens that while focusing the terahertz radiation, is basically losing 30% of radiation because these are not coated lenses. So in reality, here our optical to terahertz conversion efficiency was 12%, while we lost 30% through our lens. So this just suggests that if we can come up with approaches to squeeze light more and more into the nanoscale, where it can have more strong interaction with the semiconductor in close vicinity to terahertz antenna, we can increase this optical to terahertz conversion efficiency further and further and get closer to that limit that we mentioned, can be even more than 100%. But one challenge I have to mention is that as we squeeze light deeper into the nanoscale, plasmonic loss is another challenge that we have to deal with, which I explained what are the approaches that we use to reduce plasmonic losses. So one other particular type of plasmonic terahertz antennas that we have been using for a variety of applications, and I would like after this to dig more into the applications, has been an array of nanoantennas that we stack together in a configuration that they're periodic, and when we shine light with the right geometry, we can excite surface plasmon waves and confine light and photo-generated carriers tightly next to the antenna. So in this scheme, we gain two benefits. One is that our antennas are very short compared to wavelength. As a result, their radiation bandwidth is very broad. But you might say a Hertzian monopole should be very inefficient radiator, which I agree with you. But because we can stack multiple hundreds and thousands of these nano antennas next to each other and shine light on all of them at the same time, and in far field add the radiation constructively, effectively we can get very efficient radiation comparable with resonant lumped antennas. So while this technique offers high efficiency and broadband operation, another major advantage is that as we want higher and higher terahertz power, we can increase the area of the device larger and larger and pump it with higher and higher optical beam without having any issues like thermal breakdown and carrier screening that conventional designs have, because all the design is scalable according to the geometry. So through this scheme, we are getting record high terahertz powers. So here, for example, up to 150 milliwatts, we are getting 3.5 milliwatts terahertz power. Actually, with higher optical powers, we have reached 7-8 milliwatt terahertz power as well. But as I mentioned, the radiation is very broadband. And in time domain, we can get very short pulses that can be used for pulsed imaging and spectroscopy. This process is totally reciprocal, like any other photoconductive terahertz antenna. So here we have specifically engineered the nanoantennas this time to be Hertzian dipole nanoantennas, so that we can not only confine light very tightly at the tip of antennas, but also we can interact the received terahertz radiation at the same tip with a very strong spatial overlap. So here in this graph, you see that when I use the nanoantenna arrays I showed in the previous slide as terahertz emitters, and this nanoantenna array as terahertz detector, we can get very broad spectral bandwidth in the terahertz radiation with signal to noise ratios exceeding 100 dB in a snapshot. So for example, here there is a spectroscopy experiment that we did, I'm very excited about. Here we placed an ammonia gas cell along the terahertz beam that we generated that had a 1.5 centimeter length. The amount of ammonia we carry in this gas cell was part per million concentration. This is very close to amount of ammonia we carry in our breath. So very low concentration. So you see that after placing the gas cell along the beam path, the red graph, we are able to detect all spectral signatures of ammonia all the way from lower terahertz past 5 terahertz frequencies. Again, I want to mention this is in a snapshot detection. This is having a very high specificity because we are detecting gas based on specific unique spectral signatures that no other gas has. And specifically, I want to mention the large dynamic range we have in this detection. It's 140 dB. So this is very specific, very important because, as I said, for example, apart from other gas sensing applications, this allows us to analyze our breath. A lot of health complications like kidney disease, liver diseases carry indicators in our breath, ammonia, acetone, other kind of gases we have. And although scientists have been aware of the strong, the richness of the information we carry in our breath as a potential non-invasive way for early detection of some diseases, because of the lack of these kinds of gas sensors with high sensitivity, we were not able to have such sensors. And that is a direction that my group is very eager to explore with these spectroscopy systems. One other point that I want to mention, that these nano antenna arrays that I showed you can generate very high power terahertz radiation broadband, can be also built in a totally non-biased in a passive way. So the previous designs that I showed, as if you remember, we were applying a bias voltage to accelerate carriers and generate current that were fed to the antennas. But sometimes, for example, when we want to operate at telecom wavelengths that give us very compact systems, the band gap energy of semiconductors should be short, which means that our semiconductors become much more conductive. When a semiconductor is conductive, that's the problem for photoconductive antennas. That's because when you want to trigger them with light, apply a bias, and generate a photocurrent that gives you terahertz radiation, the low resistivity, high conductivity of the substrate generates a lot of heat and doesn't allow you to really accelerate carriers fast. That's why telecom compatible photoconductive antennas have generally poor power and poor efficiency and lifetime. So here we have studied materials that have naturally induced electric fields in them so that we don't need to use any external bias voltage. In particular, most semiconductors have a built-in electric field naturally formed on their surface. When you have a crystalline structure of a semiconductor, when you abruptly terminate it on the surface, the atoms don't have other atoms to bond to. So they have these dangling bonds, and these dangling bonds pin the Fermi energy level to a level not dictated by bulk semiconductor. For example, here in indium arsenide, naturally the Fermi energy level is pinned above the conduction band because of the surface state that dangling bonds introduce. Now, if I deliberately, while I don't have any control on Fermi level on the surface, but I have control on the Fermi level in the semiconductor, if I very highly p-type dope my indium arsenide substrate, I can push the Fermi energy level below the valence band. And since in equilibrium, Fermi level is supposed to stay flat, that causes a very sharp band bending in the semiconductor that translates to a strong field, electric field that can naturally form there. So these fields can be used, and these fields can be very strong. For indium arsenide in this case, it can be even stronger than breakdown field in indium arsenide. But since there is no path for current to flow through, it cannot break the device. So we were very eager to use these naturally induced built-in electric field at the surface, but there is a problem. They're very shallow. If I shine light, a very small portion of my light interacts with them. How can I use it for wavelength conversion? Now plasmonic nanoantennas come in place. With plasmonic nanoantennas, when I shine light on them, I can excite surface plasmon waves, and in fact, I can bend light to go sideways and efficiently couple to these surface states and use them for wavelength conversion. So this is the specific implementation we use for these passive optical to terahertz converters. We have these nano antennas that a unit cell looks like this. The substrate is engineered so that we have a very strong band bending at the surface. As you can see here with my arrows, I'm showing the band structure where we have a very strong band bending at the surface, and the colors show the strength of built-in electric field. At the same time, we engineer the geometry of these antennas so that at our optical wavelength of interest, which is telecom, it excites surface plasmon waves and couples light right under these nano antennas. And we play with the geometry so that we can maximize the spatial overlap between the light intensity and built-in electric field to harvest carriers in the most efficient way. So here we generate electron hole pairs with the under the antennas with the built-in electric field. They're swept to the antennas. They generate a photocurrent that radiates, and in far field, the radiation of all of them adds up constructively. So this is a totally passive technique, and because the radiation comes from a large array of nano antennas, there is really no specific requirement for focusing the beam, specific angle of the beam, and alignment. So we literally can place this chip, we can glue it at the tip of a fiber to get terahertz radiation out of it. So now we have a fiber that when we couple light, we can get terahertz radiation out of it, as compact as it can get. So I must mention that compared to other passive optical to terahertz converters that are either through nonlinear optical methods, photodimmer effect or spintronics, this method is very simple. It doesn't need any high intensity light, high focusing, high energy lasers that they need, and this technique doesn't need. Because radiation comes from nano antennas, but engineering the shape of nano antennas, one can manipulate the polarization and spectral properties of radiation. Here I'm using basically nano grating. So the polarization, as you know, is linear, but one can imagine that my nano antennas can be in different shapes, for example, in a spiral shape. So through that, I can convert linear polarized light to circularly polarized terahertz radiation, or I can engineer nano antennas so that I can tilt the face front of the beam. So there are so many things we can do with this platform that other passive optical to terahertz converters don't offer. And I will also, I don't know if I have a slide on it, but in case I don't have, just want to mention the optical to terahertz conversion efficiency that we get through this approach compared to other passive converters is much higher. Compared to nonlinear optical processes that are generally used, is 4 orders of magnitude larger. And look at the simplicity. As I said, we can literally glue the chip at the tip of the fiber to get a very broadband radiation right out of the fiber. I'm not sure if you have seen the experimental setups that are used for nonlinear terahertz generation. They are seriously complex. They need very high energy lasers that here we are not needed. Here we have a fiber laser, everything within a fiber. They also need very specific optics to focus beam to nanoscale, to very small dimensions to get very high intensity. A lot of times to match the momentum of light and terahertz, they have to do different phase matching, tilting the face front of the beam that we don't need there. In some cases, like spintronic, magnetic field is needed. So in general, this approach not only improves the efficiencies, but also is very easy to use and very compact. I have to mention that as I said before, the 2D plasmonic structures that are on the surface, it can help enhance light matter interaction, but still 3D approaches that we can recycle light penetrating deeper in the substrate, can be even more efficient. So before I showed you a scheme where our plasmonic structure was 3D, and I showed that we can enhance optical to terahertz conversion efficiency up to 3 orders of magnitude. But I also cautioned you that if I squeeze light more into the nanoscale, I have plasmonic losses that can also reduce my efficiency. So to tackle that problem, here we have taken a different approach. Instead of using a 3D plasmonic structures, we use 2D plasmonic structures integrated with a 3D plasmonic nanocavity, meaning that here we form a cavity that on one side we have a distributed Bragg reflector that is totally dielectric, grown with our semiconductor, that acts like a mirror on the backside of our chip. And we place our metallic nanoantennas that are plasmonic on top. So this way we form a cavity that on top is bound by these nanoantennas, and on the bottom it is bound by this Bragg reflector. So this way we recycle and confine light into a very small area, volume, that carriers are very close to the nanoantennas, so they can couple efficiently to generate or detect terahertz radiation. So through this, we were able to show very similar enhancements in optical to terahertz conversion efficiencies by another order of magnitude compared to designs that don't have the back reflector. But the more exciting thing I want to mention here is that we can achieve similar performances this time with very low optical powers. For example, here we have a detector that is based on a nanocavity, and compared to a more conventional design without a nanocavity, offers very similar high dynamic range broadband performance, but it only takes 0.1 milliwatt optical power. And the reason it's significant for us is that now for the first time, the power budget of a detector is so low that now I can think of putting detectors in an array and make a focal plane array for the first time to do multi-pixel time domain terahertz imaging and spectroscopy. So here is the implementation of our first generation plasmonic focal plane array, where each pixel of this detector array consists of the same nano antenna. So each pixel is not different, but now we are putting it in an array, and through a set of multiplexers, we are reading out data very fast. So you can see in front of terahertz and optical beam, although from a center pixel to a corner pixel, our intensity is dropping because the intensity is lower, but you see that we can maintain a very broadband and large dynamic range response for all pixels at the same time, while here we can cover 4 kilopixels. This is an exciting area for us, that now we are basically working on increasing the number of pixels to have even megapixel arrays, and we are combining it with different super resolution algorithms to even push the resolution limits beyond what basically conventional diffraction limited optics can offer. So in general, these kinds of plasmonic sources and detectors have enabled many applications in my group, many of them that are done in collaboration with other groups. For example, we have been collaborating with Washington Burn Center to use our sensors for burn wound characterization. In fact, terahertz waves are great basically indicators of hydration, because water absorbs terahertz waves a lot. And when you are dealing with assessing the burn wound severity, it's very important to be able to measure hydration, see how far the burn tissue has propagated, how close to bone it is. And since our terahertz devices can have higher dynamic range, you can see deeper in the tissue. So that has been an application that are now using clinics on patients in Washington Burn Center. Or in other applications, we have been working with different industrial partners and Department of Energy research labs to assess the health of different energy products like battery electrodes, fuel cells. These are heavily carbon-based coatings that are placed on these layers and on electrode layers, and there are different defects that can be formed, like cracks, voids, pinholes. But because these are black, normal cameras cannot pick up these defects. Not only that, each layer that we put on these battery electrodes and fuel cells have to have specific thickness to give the best performance. If those thicknesses are wrong, again, regular cameras cannot see. X-rays are very slow. So right now, with terahertz, we can see these defects with much better sensitivity. Since we have focal plane arrays, we can do imaging very fast. And you can see even from cross-section, we can measure the thickness of the layers, see if there are abnormalities and non-uniformities through this approach. We have also used our terahertz imaging systems for inspection of the different medical implants. Here, you're looking at a dental implant, in fact, a dental bridge that was built in a lab in our dentistry department. So you can see that what technician sees under microscope looks very well intact. It is in X-ray reimage that you see some sharp edges, some density variations, but it is the terahertz image, pulse terahertz image, that gives you layer by layer information of the object that really reveals, for example, a void on the backside, a crack in the middle, things that even X-ray cannot show. Also, we have been collaborating with US Department of Agriculture to use our terahertz scanners to detect different aflatoxin types in agricultural food products. So both imaging and spectroscopy of both these pulse systems help, because on one hand, most of these toxins are introduced by insect damage. So with terahertz imaging, we can find potential insect damage. It has the right resolution, but also we can detect spectral signatures. So that has been used. And I have to say, currently, there is no non-invasive way for detecting aflatoxins. So this is the direction that our collaborators are very excited about, because it can allow high throughput inspection of all products. So while I mentioned our multi-pixel terahertz imaging systems, and I mentioned our effort to push the resolution, to push the bandwidth, I must mention that AI also brings a lot of new functionalities that can simplify some of the functions that we get out of this system. So in this work, we have collaborated with Professor Ozcan's group at UCLA, where they have engineered specific diffractive neural networks that are meant to basically be trained according to specific classes of objects, here fashion items, and they're designed such that when you shine them with terahertz radiation that carries information of the object after interaction with object, depending on the object, this diffractive neural network diverts terahertz radiation to specific spatial positions where we can just have a decision of 0 or 1. Did I detect this type of object, or did I detect the other type of object? So this classification system can be very fast. It literally works at the speed of light, because as a wave passes through these diffractive optical neural networks, the computation happens. Of course, the neural network is trained with items of this category. And this way, we just spatially need to see where the terahertz wave went with very low demanding capability on the focal plane array to basically classify the object. So we have applied it to different fashion items. You see different on the type of the object, whether is it a shirt or trousers, we can classify it, or if it is a handwritten digit, again, no matter who wrote it, we can classify those objects. In another work, again, in collaboration with Professor Ozcan's group, we have looked into, instead of spatially coding the classification data, coding it in the spectrum of terahertz. So here we have very short terahertz pulses in time, which in frequency, they're very broadband. So in this work, Professor Ozcan's group have designed these diffractive neural networks, trained them so that depending on the shape of the object, the information is embedded in the spectrum of the radiation. For example, for this object, all the information goes to the first frequency band around 1 millimeter and other frequencies. So this way, even with a single pixel, we can classify objects, and in fact, even a focal plane array won't be needed. And I must say that these diffractive neural networks have been very efficient to introduce other functionalities. For example, spatial beamformers or pulse shapers that are very easy to get in the optical domain are very hard to have in terahertz, like spatial light modulators with the capabilities we have in optics don't exist. But with these diffractive neural networks, again, through collaboration with Professor Aljan's group, we were able to basically do pulse shaping. For example, here we get a very short pulse, which is a very broad pulse in the frequency. And we are able to basically get a chirp pulse with different timing and a different spectral resolution. And also, for example, we can do a wavelength division multiplexing and so on. Things that are very easy to do in radio frequencies, millimeter wave and optical regime, but in terahertz, the tools were not existing before. So before continuing, can somebody remind me of how much time I have available?
Simona, we can, we have 34 minutes in total, but we can leave some time for the Q&A.
Sure. So maybe another 10 minutes?
10 minutes is excellent. Yeah.
Okay.
Perfect.
Thank you. Okay, so in the remaining time, I would like to mention one application, another application of these plasmonic photoconductive antennas, specifically for spectrometry. By spectrometry, I mean passive spectral sensing. If you remember in the beginning of my talk, I mentioned that more than 98% of the photons that exist in our universe that carry a lot of information about galaxies, stars, planets lie in the terahertz region. And obviously, I cannot actively sense the chemistry happening on these planets or other galaxies. So because stars and sun and heated environments exist, these regions in space naturally get blackbody radiation that basically excites and carries the spectral signatures of gases in these environments that with passive spectrometers, either spaceborne or earthborne, by looking at those spectral signatures, astrophysicists get information about how, for example, stars are formed, what kind of chemistry is involved, how planets are formed, and so on. So generally, the receivers or passive spectrometers they use generally are heterodyne receivers that I'm sure many of you are familiar with. Basically, if you want to detect a terahertz radiation, if you don't have excellent electronics to process it, one good way is to mix it with a local oscillator signal close to your terahertz frequency. And the mixing product will be in a much lower frequency where you have excellent electronics like electrical spectrum analyzer to analyze these spectral information. The issue is that when it comes to astrophysics studies, these signals are extremely weak. You really need quantum level sensitivities. And if you want quantum level sensitivities, you usually end up having mixers that are mostly superconductor based, so they need cryogenic cooling. And we end up having instruments like this. So this is the cryostat of Herschel mission. Herschel Observatory actually was a €1 billion terahertz observatory that is finished right now. In order to cool the terahertz heterodyne receivers, it carried more than 2,000 liters of liquid helium that weighed 335 kilograms. And just I want to mention the rest of the instruments were 426 kilograms. So just cooling had a big, basically, impact on the system. Not only that, this €1 billion observatory, once it was launched, liquid helium started boiling off. I mean, everybody expects it. So it only could work for 22,000 hours, after which the system was basically not useful. So just imagine what would have happened if this €1 billion observatory did not require this cryogenically cooling. It could be lighter weight, less expensive, maybe it could carry other instruments, and more importantly, it could be existing today to do more observation. So this cryogenic cooling has an impact on these systems. So we have come up with an alternative approach that can offer very similar sensitivities at room temperature. So this is the concept. So we build a heterodyne receiver, but this time an optical heterodyne receiver. So what we do different compared to a conventional electronic heterodyne receiver is that we replace a mixer with a photomixer, and we replace local oscillator, electrical local oscillator, with an optical local oscillator. How does it work? Our optical local oscillator is basically two lasers, CW lasers, with a terahertz frequency difference. We combine them in a fiber. So they beat each other at terahertz frequency. So our photomixer is the same device you have seen, a photoconductive antenna connected to a terahertz antenna. So when we receive, when this light is absorbed in the semiconductor, it generates electron-hole pairs. Electron-hole pairs follow the envelope of the optical beam. So if this local oscillator is at FLO, the concentration of carriers is modulated at FLO. Now we receive terahertz radiation. Let's say it is at F terahertz. Now we have a semiconductor material that carriers, their concentration vary at FLO. The electric field that drifts them is fluctuating at F terahertz. So the drift current is the direct mixing product of carrier concentration and electric field. So here we have a direct mixer that mixes the local oscillator frequency with terahertz frequency, and down converted signal is routed out of our mixer. So in this block diagram, for example, if this is the spectrum at terahertz we are interested in, we park our optical beat frequency in the range that we are interested in, as I'm showing with omega beat. Then if my terahertz signature is at a certain frequency difference from this omega beat, we down convert that difference frequency, which can be very low in frequency in gigahertz range, to low frequency and detect it with low frequency, few gigahertz electronics. So this way we gain multiple advantages. First of all, we can use very strong intensity optical local oscillators, where terahertz local oscillators cannot offer very high power. So we can increase signal to noise ratio of the system. Also, because by tuning the wavelength of one of these CW optical beams that beat each other, we can tune the terahertz frequency a lot. We can basically move this beat frequency along the spectrum and scan a very broad range that other systems could not scan. So here is the experimental results of the first prototype of this heterodyne receiver. And this is the experimental setup where we use two CW lasers to excite it. So these heterodyne receivers, their sensitivity is usually assessed with their noise temperature, either double sideband or single sideband, depending on which sidebands you keep in your detection. So obviously, the lower noise temperature is, you have a better and better sensitivity. So as you can see, the room temperature heterodyne receivers that were developed before based on, for example, Schottky mixers, they have very high noise temperature. They're not sensitive enough. Superconducting mixers, high electron bolometer mixers, can offer quantum level sensitivities, but I mentioned they're cryogenically cooled and their bandwidth is also limited. So here the black data, which are the results of our photomixer, as you can see above 1 terahertz offer the best sensitivity, while they can reach around 3 terahertz, they can offer 3 times quantum level, while these are fully room temperature operated. And also I want to mention that all the data over all frequency ranges that are measured are with only this one instrument. Only we tuned the wavelength of one of these lasers. So we cover a bandwidth of more than 5 terahertz. So this can really simplify future spectrometers for astrophysics studies. Now we are actually building a specific instrument to be installed in Henrik Hertz telescope as the first in-field demonstration using this technology. And I skipped that. In the remaining time, I just quickly want to mention that ultimately, although many of these applications like astrophysics studies and basically scientific studies that are done in the lab or factories, industrial environments, do not mind to have a little bit complex systems. But at the end of the day, we want to bring terahertz technology to everyday application, like where cell phones are in our everyday life. So that really requires integrating light sources and these photoconductive antennas on the same chip. So in this regard, we have had different collaborations with different laser experts. For example, in this work, we worked with Dublin City University, where they have this dual DFB laser that gives us a terahertz beat frequency that is tunable. So we hybridly combined it with our terahertz lasers, with our photoconductive terahertz devices, and we were able to achieve very similar terahertz powers that we were getting, but now through a very compact flat platform. Or in another work, we collaborated with Professor Chi-Wei Wang at UCLA, where he has these silicon-based micro-ring resonators on chip. And through that, he can generate these frequency combs that can be engineered to beat each other at terahertz frequencies. So again, the same story, we hybridly combined their lasers with our terahertz devices in a very compact setting, and we were able to get very high terahertz power, but this time through a compact setting. One unique thing about their lasers is that when you deal with frequency combs, you might have fluctuations because of temperature variations, but because comb lines move together, you can get very stable terahertz beat. So here you see that we can get very narrow line width in our terahertz radiation with stabilities that can even go to sub-hertz level while giving such a narrow line width. So currently, actually, this is a very active area in my group where we are working on now monolithically integrating lasers with these terahertz devices on the same chip for a variety of applications. So in summary, we have worked on optically triggered, optically empowered terahertz devices, sources, detectors, imagers, and spectroscopy systems, and to make light matter interaction much more efficient and increase the efficiency of these devices, we have seen a lot of potentials in use of plasmonic nanostructures. We have also worked on different reconfigurable metasurfaces for manipulating spectral and spatial properties of terahertz radiation. I didn't have time to discuss it, but please check the publications from my group. And finally, I would like to thank my group members and sponsors for making these possible, and would be happy to take your questions.
Oh, thank you, Mona. Such an impressive area, and a great collection of all these contributions. Very impressive.
Thank you.
So,
Thank you, Professor Jarrahi, for inspiring presentation.
Thank you.
It was a pleasure to host you in this event. So I'm just going to ask our participants, please feel free to drop your question in chat box, or please you can ask a question by unmuting yourself.
Yes.
Mansoor, if you let me, can I use this time to ask a quick question?
Please go ahead. Time is yours, Professor.
I don't want to.
Thank you very much. Thank you. I see you.
So Mona, it is impressive, especially in astrophysics and these radio astronomy, even in those areas there are applications. I was wondering if you how applicable do you see the use of terahertz bands for communication purposes in space networks? Because now there's all these satellite mega constellations coming up, and then we will also need to in a short while need to worry about communications on Moon, on Mars, and other planets. So do you think there is a potential for that in that area?
Definitely. I haven't personally worked on that area, but it's definitely it is a very promising area because of a few reasons. One, well, communication at higher data rates, even on Earth, is attractive, but on Earth we have atmospheric losses which don't exist in space. So obviously some of the challenges are gone, and terahertz would be the loss issue does not exist there. Another important feature of terahertz communication is that it can allow you to work with more compact antennas, and reducing the feature size of antennas obviously is something that space-borne applications are interested. Of course, there are very nice technologies for foldable antennas, foldable devices. We see in the new Hubble telescope how a massive mirror is really compact when it is carried there, and then it is there, but it still can very much simplify the electronics that are used.
That's excellent news for the new space communications era. So Mansoor, do we have any questions?
Yeah, I'm looking for questions, but I believe everybody enjoyed. Oh yeah.
Or not listening.
Yeah, but I think maybe the topic was pretty tough to digest, so that's why. So yeah, we got one question. Yasser asks, as you mentioned, integrating power sources is possible into terahertz devices. However, in electronics-based techniques, also high efficiency are achieved. In your opinion, what will be the future of terahertz handheld, commercial sensors, or communication and imaging?
A very good question. Actually, I always say there is no winner solution for terahertz systems for whatever application. So on low frequency side, we have electronics. So they cannot cover the entire terahertz band. They cannot do spectroscopy at 5 terahertz. But if lower terahertz frequency ranges are needed, like below currently 300 gigahertz, they definitely are great solutions. They benefit from compactness, very easy fabrication, compatibility with other electronics. So on the other hand, there are things that they cannot do. I think at the end of the day, it is application that says what kind of instrument tool set will be needed. That being said, all of these areas are very quickly evolving. I mean, I don't know, in 10 years when we have this discussion where electronics-based devices are, where photonic-based devices are, we know fundamental physical limits, but at the current state, for example, for terahertz communication systems below 300 gigahertz, I think electronics are winners. If sensing requires spectroscopy below 300 gigahertz, they win. But if one wants to detect spectral signatures at 5 terahertz, 3 terahertz, electronics, they cannot. I mean, there's no information for them to pick up. So it really, really depends on the application. And we have quantum cascade lasers, something that I didn't have time to mention. I mean, that's an entirely different story. Is actually basically a solid state laser that lasers terahertz radiation. It has a cryogenically cooling requirement, but there are ways for example, using infrared quantum cascade lasers and using different frequency generation to convert their radiation to terahertz frequencies. So there are a lot of tool sets that one has to really choose the best for their application.
Great, thank you for your answer. Yeah, we got one more question. It sounds a bit personal, but I'm going to ask. Christine asks, I would like to know that optical metasurface is also in your field of research or not?
Optical metasurface. So as I mentioned, as you see in this slide, we have worked on terahertz metasurfaces. I didn't have time to talk about it, but as a highlight of some of the directions of my research, I put it in this concluding slide. So metasurfaces are definitely great ways to manipulate spatial and spectral properties of electromagnetic waves in unusual ways that nature doesn't offer. We have benefited from that as well. As I said, a lot of tool sets that other frequency ranges enjoy, we don't have it in terahertz frequency range. For example, for intensity modulation, here I'm showing a work where we built a metasurface where an array of MEMS switches were embedded in it. And by switching on and off these MEMS switches, here you see a zoom in version of one switch, we were able to change the configuration of the metallic structure we had there. For example, changing it from a capacitive mesh filter to inductive mesh filter. And that was changing the scattering parameters, and that was allowing us to do broadband intensity modulation of terahertz radiation, of course, with the speed that MEMS limits us to. Or in another work, we embedded phase change materials, like in this case, vanadium dioxide, in a resonant metasurface and around the resonance frequency. By controlling the electric signal that basically was heating our vanadium oxide, we were able to change the phase modulation in each pixel. And by controlling that distribution, we are able to tilt the phase front to be able to tilt the terahertz radiation. There are many other excellent work that is done by other groups for specific manipulation of spatial properties for different types of lenses that have been developed. And this can be also applicable to the optical domain. We have a work, like I showed a lot of work where we use these plasmonic gratings to enhance light intensity next to the antenna. Other types of metallic periodic structures have been also explored by my group that, for example, were more 2D symmetric. They did not have polarization sensitivity. So metasurfaces can be helpful both on the optical and terahertz front.
Great. That sounds good. Thank you. Nazanin, just a quick question about the diffractive neural network. Are the information carried by terahertz pulse? And does it mean that using terahertz, you are using frequency multiplexing to process information with neural network?
I am not sure if I understood the question. Can you read it again?
You have access to chat box if you don't mind. Just
sure.
It could be my fault that I just, can't transmit in terahertz domain.
Okay.
Because I'm working with the low frequencies.
No worries. No, I think it was a long question. Maybe I missed it somewhere. Yeah. Let me find the question.
And Nazanin was like.
Okay. No, it's not this. Let me enlarge my box.
Yeah. Okay, what I can do, I'm going to.
Is it the one that says just a quick question?
Yeah, there
Oh,
is another quick way, like I can.
No, I can answer it. Just a quick question about diffractive neural networks. Are the information carried by the terahertz pulses, and does it mean that using terahertz you use frequency mode? Information is carried in the terahertz waves. So terahertz waves here are like carrier signals. So terahertz waves interact with the object. For example, in the classification case, you shine terahertz on the object. So object shape is already embedded in the terahertz frequency, in the terahertz wave. Now, one way to image that object and classify is to give it to a focal plane array, reconstruct image, and then say, is it an image of a trouser or a shirt? But here, what we have done is that this classification is done very fast through diffractive neural network. So that neural network is basically trained so that depending on the phase front and shape and distribution of the terahertz radiation, it directs the beam to one spatial position according to particular shape it was trained for. So that, and the output, you can just say, was the object that received terahertz radiation class 1 or class 2 or class 3? I hope that answers the question.
Yeah, I hope so. Yeah, I think that was the question. There is one more from Youssef. He asks, I was wondering if you could a little bit more elaborate on your solution for creating on-chip terahertz source. Do you follow a solution similar to those solutions that Professor, there is a name of Professor that at UCSB, is that the hybrid or heterogeneous solution? I think that's the question, like, is the solution that you're proposing for on-chip, is it heterogeneous or hybrid?
What we are looking at is monolithic integration. Like if I know the name of professor, I might, Professor Bowers. Honestly, I don't think Professor Bowers is working on-chip terahertz. I mean, Professor Bowers works on on-chip laser sources. Well, the laser sources that we are currently working on, I don't think resembles his. We are using, there are two categories we are looking at. One are frequency comb lasers through micro ring resonators. The other category are PD symmetric lasers. For PD symmetric lasers, we are collaborating with Professor Merced Hajabi Khan at USC. And for frequency comb lasers, we're collaborating with Professor Chiwei Wang at UCLA. But in general, any kind, I mean, I'm not saying these are the only solutions, it's ongoing research. Any kind of optical laser that is on-chip based can basically be engineered to produce terahertz frequency information embedded in it. And there are so many different lasers, including the ones that Professor Bauer's group is working on, that can be used for this purpose.
Great. Yeah, one endorsement from Murtaza, like he says, I couldn't understand much, but I enjoyed. So I think he is like me because I had the same feeling. I enjoyed the talk, even though I couldn't understand, I couldn't grasp the whole information. Anyways, there is one more question from Ali, asks, have you ever tested entanglement on the terahertz output wave of your structure? Have you done any research on this topic in general?
I haven't. It's a very interesting topic. I would love to. I've thought about it, but haven't done anything yet.
Great. One question from Kinga U. Thanks for the interesting topic. In slide 14, 7.5% conversion efficiency seems not very high. Why there was so big loss? Why do not use other substrates such as impede, SiC? Thanks.
Okay, so the person who asked this question hasn't worked in the terahertz domain. That thinks 7.5 terahertz is not high. actually, this is a still record high, and others are way lower than this, if not another order of magnitude. So
I'm
that's
sure
the
it
first.
is. Yeah.
But what was the next question? Like, how can we improve it? What was the offered approach? What's the source of
Like,
loss? And then
INP, like such as why do not use other substrate like such as INP, SIC? I'm not sure SIC stands for like I don't know, as
silicon
self-interference.
carbide, indium phosphide. Okay. Well, first of all, silicon carbide is not a direct band gap semiconductor, so that won't be helpful for these photoconductive devices. Indium phosphide, compared to gallium arsenide, has a lower mobility, and resistivity is also lower. So that was the reason that so the loss here is not because of the semiconductor band gap energy or type. This is the inherent basically conversion efficiency that you have. So the thing is that in your photons, in your light, you have certain number of photons. You want to compare all those photons to electron hole pairs, and you want to transit those electron hole pairs to the antenna in an ultra fast way. So if all of them really appear on the antenna simultaneously, you can get very perfect efficiency and convert them. But you have this transition from semiconductor to metal. So you have to somehow squeeze light as close to antenna as possible. And there's a limit, physical limit, how much you can squeeze light. So
yeah, indeed, every percentage matters, a lot of efforts. That's without any hesitation. So one more question. Thanks for exciting work and nice presentation. I see that Terahertz work in direction imaging and spectroscopy. How do you see Terahertz for wireless communication link? How do you evaluate it versus wireless optical communication? I think it's about visible light communications. How do you compare it with the visible light communication?
Right. There are pros and cons for both of them. First of all, terahertz communication, well, we discussed space-borne application, but now talking about earth-borne application. Terahertz communication in my view, won't replace our cellular networks because of atmospheric losses. It's good for short-range communication. That includes indoor communication, like highly crowded environments like conference center, stadiums, shopping malls, those kind of areas that you need to cover very high data rates, or for backhaul, basically for data centers that you want, or data kiosks as they have in Japan, that you want to transfer massive information over a short range. Now, compared to optical systems, optical systems are more affected by obstacles along the way that can basically block the beam, especially in these indoor communication systems. You have people moving, objects moving. In optical domain, because the process is so directional, you totally lose the beam if an obstacle is along the way. But in terahertz, you can still rely on reflections from non-line of sight paths to be able to get the data. In terms of bandwidth, still optical communication systems, if you really want to go to terabit per second type of data rates, you need some sort of terahertz modulation mechanism. So they still would share a lot of common components, and they will have similar frequency limitations. One thing that they benefit a lot in the optical domain for increasing the channel capacity is wavelength division multiplexing. In terahertz, it's not used yet, but that's just a practical issue. Like there is no problem to have a multi-frequency terahertz source or an array of sources that cover different spectral bands.
Great. Thank you. Elaine asks, have you considered terahertz for NIGM, non-invasive glucose monitoring?
I haven't. A lot of work has been done, and I think everything is known about it right now. Glucose, when it is not basically dissolved in blood and in water, there are very well-known spectral signatures of terahertz, and that created a lot of excitement in the community. Obviously, everybody looked at blood, but when it gets dissolved, that crystalline form goes away and the signatures go away. So in terms of practicality, doesn't seem like there are much opportunities out there. I don't know, with new AI based data analysis, maybe there are ways to find more signatures. But that has been based on other group studies so far.
Great. Thank you for your answers. I think we have addressed all the questions. So any other question? If no, I'm going to hand over again microphone to Dr. Güneş for concluding remarks. Dr. Güneş, floor is yours again.
Thanks, Mansoor. We are right on time. And I am so glad that we finished with a positive note, because I also had another question on the use of WDM for terahertz and how we can squeeze the multiple carriers like to one another to see to improve the efficiency. So it's it looks very promising. Thanks a lot for this inspiring talk, Mona. We are delighted to have you as our speaker, and thanks a lot for I would like to thank everybody for their participation and their interest as well. I guess this concludes our seminar for today. Thank
you very much for having me, Güneş, for your invitation, Mansoor, for moderating the seminar and questions. It was my pleasure. Hope some of you could use some of the topics that I discussed today. I know it might not have been in line with some of the research that everybody was doing here.
Yeah, that's the interesting part of these events, that a lot of people get inspirations and motivations from the scientists like you, that they could like choose their next career. So that's like one of the points in our events, that we are able to inspire a lot of people from bright mind by inviting bright minds and giving talk in different domains. And thanks for sharing the knowledge. It was really interesting topic.
Thank you. Thank you.
So just one last question. Are we allowed to share your talk with our participants later?
Sure, no problem.
How about public? Can we share it in public?
Actually, this particular presentation is probably on my website already.
Okay.
So,
okay.
Sure. Yeah.
Okay, it's okay. Yeah, we just needed to confirm live while we have you. So that's interesting. So one more time, thank you, everyone. Thank you, Dr. Güneş, for hosting these series of events. So we almost finished third session. Looking forward for the next session. It was really a successful event. We had almost 50 people on board from the beginning of the event till the end. So we very much look forward to see Professor Jarrahi, hopefully one day in person after this COVID situation. And so, yeah, who knows, like one day maybe like we are going to have an opportunity to host the in-person events in Montreal.
I look forward to it.
Thank you, everyone. Thank you for participants. We will get in touch with you for the complimentary information. So I'm going to stop the sharing.